Okay, howdy, Ags. You guessed it. Yes, it's another episode of Biomechanics, Exercise Biomechanics. So today we're getting at really, I think, the core about how people move, and it's all about torque. So we're going to probably have a relatively short lecture, actually a series of lectures related to torque and torque applications. So what's torque about? Well, really, all human movement, whether we're lifting a weight, whether we're going to take a drink, combing your hair, climbing a set of stairs, throwing the shot put, doing an amazing gymnastics move like the GOAT, the greatest of all time, Simone Biles here, greatest gymnast. It's all about producing an off-center force. And what do off-center forces do? Well, they can produce rotation, whether it's the gluteus and medius producing abduction of the hip, or someone trying to throw a curveball and having their fingers slide off the ball, producing a lot of rotation. So it's all about an off-center force. It's actually really easy to do. In fact, it's more difficult to produce a force directly through the center of an object. So our body takes advantage of this, for example, for really all of our movements involving, first of all, muscle contractions. When a muscle tugs on a bone, it can produce torque. It can also help to, especially if there's a co-contraction, press the articulating bones together at a joint, allows them to rotate freely, but with enough compression along cartilage that is bathed in synovial fluid, it allows that joint to move freely through rotation. And that's what muscles do. They produce rotation or torque. They're able to also produce stabilization of bones and joints. So it's an off-center force. Some classic examples here. So you've seen Simone. Here's a shot putter. They've got that shoulder joint angle getting just about there. So that way they can maximize their kinematic chain, throw that shot put maybe 60, 70 feet. There we go. It's all about producing rotation. So if you can produce, oh, it even hurts to try to do that, the type of lateral rotation of the shoulder in the windup. So you literally have this spring that's going to go. It's, in a sense, a spring with a motor on it, because we have muscles that are producing force, power, and that's going to be able to propel that ball forward. But what they have to be able to do, though, is tug on bone somewhere away from the center of a joint, axis of rotation, or body segment, so that we can produce movement. So here we see a baseball player. Torque can be expressed a couple ways mathematically. One way is to, we've shown this before, to use Newton's second law of motion, and then use the angular analog. So we'll show that in a second. The other way is to think about an off-center force. So, for example, let's pretend that we have a wrench set, a ratchet set. So the force being produced on the ratchet is some distance away from the axis of rotation. The greater this distance is, the greater the lever. Remember, a lever is a bar-like body that can rotate about an axis. So the longer the wrench is, the greater the amount of torque you can produce, because that torque is a product or combination of the force being produced and then how far that force is being produced away from the axis of rotation. So it's force times distance. The only major rule here is that the force and the distance have to be at right angles with each other or perpendicular. And if they're not, then we'll show you how to do that. We can either resolve the force vector or create what's called a moment arm, where a moment arm is really kind of an imaginary distance between the axis of rotation and then the line of force. It's the shortest distance. It's always perpendicular with the force, regardless of where the force is going. So the units for torque actually don't come from units of moment of inertia and angular acceleration. That's the angular equivalent of F equals ma, but it comes from force and distance. So in the metric system, it's Newton meters. In the English SAE system, it's foot-pounds. So we use T for torque. Sometimes people use gamma, the capital letter. There we go. So here's our angular analog for torque. So from Newton's second law, the law of acceleration, force is equal to mass. Mass is inertia, resistance to motion. That's why it's the first law of motion. It's about this part, the resistance to a change in a linear or angular velocity, and that means acceleration. So force is equal to mass times acceleration. The angular analog or equivalent is torque, which is like an angular equivalent to force. Moment of inertia is the angular equivalent to mass. And then you have angular acceleration as opposed to linear acceleration. So for Barry Bonds, he changed the game a number of ways, but in a good way, what he was able to do really effectively was take a bat and not use something like a bomb bat. This bomb bat was a real bomb with a B on the end. It didn't really go much of anywhere because it was too heavy. So he used a bat that was lighter. I think it weighed, 31.6 ounces. And he also choked up on the bat, meaning he didn't hold it against the very back of the handle right here. Moved up, and as he moved up, what that does as he chokes up, it reduces the radius of gyration. So the radius of gyration is part of the moment of inertia formula. Again, the constant has to do with the shape of the object, its mass. So Barry Bonds reduced the mass instead of using like a 40, even 46 ounce bat, which Willie Stargell used to use. We saw actually a copy of one that was being sold on eBay or somewhere. And then he choked up on the bat. So mass and the radius of gyration decreased. So that combination caused a massive reduction in the moment of inertia. And that meant he could get the bat into the hitting zone quickly. And it's all about, again, bat speed, club head speed, racket speed. It is the need for speed. Supposedly the follow-up for Top Gun is going to come out eventually once we're able to get into the theaters again. So the need for speed will be back. So here's Barry Bonds choking up on the bat. He used to stand right next to the home plate. So he would crowd the plate and get that bat across the plate really quickly. And so again, that meant he often was hit by balls because he was very close and they would try to brush him off, or he was walked, or he hit a home run. It really seemed like almost every other at bat was like that. He had a huge slugging percentage up in the 700s, I think. It was ridiculous. So we produce torque for lots of things: moving our joints, shot put, hitting a baseball, tennis ball, pretty much anything. So whether, again, it's the shot put, and by the way, again, this shot put technique, it came from the discus. The difference is because the discus, I think, is a mass of 2.2 kilograms, and we're looking at close to 8 kilograms for the shot put or the shot. We bring the shot up close to our neck to reduce the radius of gyration and therefore manage that moment of inertia. That means for a given torque, they're able to spin faster. So that's what they're trying to do, is get that really fast spin, just like the discus throwers. This is Al Order, by the way, who, let's see if I can write it in, 4-time Olympic gold. 4-time Olympic gold. Big champion. and really kind of perfected that discus technique. And that technique, as I said, if these two look kind of alike, yeah, they should. So that's where the shot put technique came from. Throwing a curveball, throwing a spiral in football, which will make it more stable in the air. I call this a gyroscope effect, because what we're doing is, there we go, needs to be that symbol. As we increase the angular velocity, and assuming a certain moment of inertia for the football, that'll increase the angular momentum. And angular momentum, it's a vector. So there's the spin, here's the vector itself. It means that football wants to stay along that axis. It's going to make it stable as it's moving in the air, so that wind, air drag, etc., will have less of an effect on that ball. Really important in months like November, etc. Patrick Mahomes, whatever he's doing in terms of throwing a football and his movement, man, he's certainly changing the game. He and Mr. Jackson from Baltimore, it'll come to me in a second, who used to play, I think, for Louisville. They're definitely changing the NFL, making it exciting. So hopefully be back in the fall. There may not be much of a crowd in the stands, but there'll be lots of eyes watching them on television if they are indeed back. Okay, so to calculate force correctly, the force and distance, the lever arm, if you will, have to be perpendicular with each other. If they're not, then we have two choices. We can, in this case, let's say we're loosening a bolt and we can't get our hand so that it's perpendicular with a ratchet. So if it's off at an angle like this, we can either resolve that force vector into a rotary component and then a perpendicular component or a stabilizing component, or we can create what's known as a moment arm. You can do either one, but it's an or, it's not an and. Don't do both. Choose one. Usually when I'm dealing with outside forces and free weights, I'll usually go for the moment arm, and then for muscles, I'll usually split them into rotary and stabilize components. But choose one, either way will work. You'll get exactly the same answer with the same units. It all works. Okay, so if I'm lifting a free weight, I almost always go for the moment arm, and that's because if gravity acts in the vertical direction, let's say I'm doing an elbow flexion exercise, if gravity is vertical, something weird has happened to my arrow here. Disappeared. There we go. Okay, moving it up like that. Okay. If gravity is acting downward, and so that's the weight of, let's say, this dumbbell or barbell that we've got in our hand, that means the moment arm has to be perpendicular to that. So it means it's horizontal. So it makes this relatively easy to set up. When we're looking at limbs and body segments, they're often the lever arms. They can also be the radius of a circle. So that really helps us with setting up these geometric models. Especially if they are right triangles, and then kind of simple arcs where we can draw in an arc length. Okay, so here's the lever arm, which would be basically the forearm and up to the hand. The axis of rotation might be a joint like the elbow joint. Here's our moment arm. So moment arm, remember, is torque arm. Moment means torque. It doesn't mean anything related to time. So moment arm, moment refers usually to bending forces or turning forces or torque. Here's our moment arm. So we can calculate that. So we have an angle theta, which of course is the deviation from horizontal. We've got a lever arm. We actually have everything we need if we know the lever arm, to calculate the moment arm. So the cosine of theta will be equal to the adjacent side, moment arm, divided by the lever arm. So that's exactly what we can plug in here. One of the things to remember as you guys are using these formulas, etc., let the triangle tell you what to do. And this sounds weird, but because sometimes when you're calculating a moment arm, that moment arm could be opposite the angle that you have information on. So don't always lock into one very rigid formula. Let the geometry tell you what to do. Let the geometry tell you what to do. Okay, so I'm going to do a problem from this. Let's say Jody is doing an elbow flexion exercise with a 120 Newton weight. The length of her forearm, we're just going to say elbow to the middle of her hand, is 40 centimeters. So I'm cheating a little bit. If her forearm's in a position that's 35 degrees below horizontal, let's find the torque. Okay, so I have the weight due to gravity. I have a lever arm. They're not perpendicular with each other, so I can't simply multiply them together. Either I could calculate a rotary force or create a moment arm and multiply by the moment arm. If someone is going through a range of motion with a free weight, like elbow flexion, what's going to happen as the forearm rotates around the hand? The length of that moment arm is going to change. If you're standing, let's say vertically, oh, there we go. Standing vertically like this, I can stand sideways, and your elbow is kind of straight, right? You're producing actually very little torque on the elbow until you lift that weight, and that moment arm actually increases and increases. As you continue with flexion, it actually gets shorter and shorter and shorter. So the moment arm changes throughout the range of motion. And that means, because the weight hasn't changed, you haven't done a magic trick, it means the torque is changing. And that also means the resistance that you feel and have to overcome with your muscles at the joint is also increasing. So as you go through a range of motion, what it means is that the torque produced by an external resistance or an outside impact force is changing. Now, the cool thing that also changes is the torque that your muscles are able to produce. So if I go through a full range of motion, it turns out the optimal angle of pull for my muscles is right about here, at about a joint angle that's about 80 degrees. So believe it or not, your ability to produce torque also increases in the middle of the range of motion, just like the ability of the torque that's produced by that free weight is changing and is kind of max in the middle of the range of motion. So you can change, you do preacher curls, you can change body position to emphasize more towards flexion or more towards extension. Those are things that you might want to be able to do as you're working through a program, and maybe emphasizing different parts of the range of motion depending upon what you're trying to do. Okay, so let's work through this problem. We've got basically a lever arm of 40 degrees, 40 centimeters, excuse me. The force arm or the lever arm here is 40 centimeters. The angle is 35 degrees, the angle from horizontal. So that means to calculate the moment arm, I can use cosine. So we've done a little bit of algebra. The moment arm is therefore equal to the length of the forearm, the lever arm, times the cosine of 35 degrees. That will allow us to be able to use the weight of the barbell. Okay, so let's crunch these numbers out. For the moment arm, we've got 40 centimeters times the cosine of 35 degrees. So it's 40 times 0.819. That's 32.77 centimeters. Okay, good. So now we can plug it into our equation related to torque. So here, torque is going to be equal to the force times the moment arm, or the weight times the moment arm. So that's 120 newtons times 32.77 centimeters. That's 3932.4 newtons per centimeter. I've converted it to standard units, and so that's 39.32 Newton meters. Okay, so that's not too bad. So in the body, adjust this a little bit. There we go. In our body, our muscles can also produce torque. The way we can represent that is to split up a muscle force vector into its two components. One that produces rotation, and then another component that actually produces stabilization, especially if it's pointing towards or through a joint. So let's do a problem. Let's say someone's doing a bench press exercise, and the pectoralis major muscle is contracting with a force of 400 newtons. If it's angle of pull, and angle of pull alpha is basically the orientation between the line of the muscle force. So if you were wondering, why the heck do we have to know origins and insertions? What good are they? This is why. Because the origin and insertion of the muscle tells you where the muscle vector is going. It's going from one tendon to the other for the most part. There's a few exceptions, but for the most part, that's what's happening. The gastrocnemius, it's going up that Achilles tendon, up the middle of the gastrocnemius and soleus towards their attachments. For the gastrocnemius, it'll be on the femur, and then for the soleus, it'll be on the tibia. So that's where your actions, insertions. They tell you how to draw these stick figures. They tell you where that muscle is pulling. We also have lots of data from real live people as well as cadavers about how that works. So when a muscle is contracting, that pectoralis major is attaching on the humerus, but some distance away from the middle of the shoulder. So there's a lever arm distance. Technically, we'll probably call this a force arm. It'll look something like that. Force arm just means this is the distance between where the force is being applied and the axis of rotation, which is the shoulder. The longer this force arm is, the greater the amount of torque. So for a given force that I'm producing, if I can double the lever arm, I double the amount of torque. So in some individuals, they actually have a greater distance between the end of that tendon and the middle of the shoulder. In some of our simian species friends, they often have a pretty large distance. They can also produce a lot of muscle force. So actually an adult chimpanzee, they're much larger than they're drawn or portrayed in the movies. Usually when they have a model for a chimpanzee, it's a 1 to 2 year old female, because they can train them and they can't train adult females. And they definitely can't train males. Males throw really bad stuff at you. An adult male is actually probably a little over, if they could stand really tall and straight, they'd be about 5 feet tall, about 170 pounds. They are not small. And they can produce lots of torque. So don't get near them. Okay, so we've got someone doing our bench press. Here's the pectoralis major muscle. It's contracting at an angle of pull of 41 degrees, right there. We've got a lever arm or force arm distance of 10 centimeters. There we go, 10 centimeters. So let's put this together and then calculate the amount of torque. So it's going to be a two-step process. The first thing we're going to do is we're going to construct a right triangle. When we resolve a muscle vector, we can move any vector component anywhere we want to, as long as it has the same magnitude and same direction. So I can move it over here, could move it back. So here I've constructed my right triangle. When I do that, the rotary force is now opposite alpha. So it means that we can use a sine relationship. So the sine of alpha is equal to the rotary component, the opposite side, divided by the hypotenuse, which is the muscle force. And then to calculate the torque due to the muscle, we're going to isolate this rotary component by calculating it here and then multiplying it by the force arm distance. So let me do this again. Copy and move this, edit it or not. Okay, we'll move on. Go, there we go. Okay, so we're setting this up. We're going to calculate the rotary component first. So we're going to take our sine equation and then multiply both sides by the muscle force. So we've got 400 newtons times 0.656, and that gives us 262.42 newtons of force. Then we're going to take that rotary force, 26.42 newtons, multiplied by 10 centimeters, and that gives me 26.42 24 Newton centimeters, and we'll convert it to standard units, which means that we've got, there we go, means that we got 26.24 Newton meters, 26.24 Newton meters of torque. So that's the amount of torque that, if we look at one arm is producing. You put both arms together, you're producing 52.48 Newton meters of torque. That's a fair amount. The pectoralis major, and I should add in, we're also using the anterior deltoid. That's a lot of muscle mass that's producing force. That's one of the reasons why, again, those shot putters are going to tilt their shoulders so they get that optimal 37, 38-degree angle. So they're producing horizontal adduction. That's the movement in the shoulder that's being produced, along with elbow extension. That's how you're getting that weight up. Okay. The next thing we're going to do, I'm going to introduce this next section, and then we're going to actually take a pause, and we're going to visit what we call lever systems. And lever systems help us to translate force into torque. So we're going to split up these torque lectures into a number of discrete but shorter sections, because this is fairly complicated stuff conceptually. So it's going to take, I think, a while for us to catch up. We probably want to do some practice problems. There we go. Move around. There we go. So hang on there. Switch sides or switch slides here, and I'm going to introduce these next couple sets of concepts, and they're going to be critical in understanding basically how human movement's occurring, how we're translating force into torque, both in terms of what our muscles are doing, and then how we're overcoming these outside forces and torques. Again, whether you're lifting a weight or throwing something or pushing something or lifting something or running, what you feel is the torque in your joints. You're not feeling forces per se, you're feeling the torque in terms of motion. You do feel, or I don't know if you sense, but in your joints, there's compression being produced. You'll feel pain if there's more shear force at your joint than there's supposed to be. And that's one of the reasons why your muscles are contracting, especially those co-contractions, to keep the articulating bones together. And if you have nice, healthy cartilage, that makes the system work really nicely and be really tight. Okay, so the next thing we're going to talk about is something called the principle of moments. And again, it has nothing to do with time. Principle of moments really means principle of torques. So a moment is your ability to produce rotation or torque. It also means the resistance against a bending force. That's actually a bending force, where you take a material and twist it up. Well, probably twisting is not inappropriate, because that's really twisting, that's torsion. But where you're taking the material and you're actually stretching it on one side and compressing it on another side. So that's technically bending. The principle of moments may look a little scary, but conceptually it's actually pretty straightforward. It says the net or total torque on a system is simply equal to the sum of the individual torques. You just add them together. The key thing you have to keep in mind is direction again. And since we're talking about the angular reference system, remember, instead of left or right, being left being negative, right being positive for the x-axis, this is counterclockwise being positive and clockwise being negative. So let's say we're looking at two people on a seesaw, and you have a fulcrum or an axis of rotation in the middle. This is actually called a first-class lever, like a seesaw. And then you have forces on either side. But what the forces are doing is actually producing torque, or turning in opposite directions. If you have someone that has a weight of 500 pounds and they're 2 meters from the middle of the seesaw or axis of rotation, they produce an equal amount of torque in the opposite direction as someone sitting on the other side of the seesaw with 1,000 pounds of weight, but only 1 meter from the axis of rotation. big person producing a huge weight, but they're not as far from the axis of rotation, so they produce an equal amount of torque. Notice the forces are in the same direction. With a first-class lever, like a seesaw, the forces will roughly be in the same direction, but they produce torque in the opposite direction. So we have to give them an opposite sign. So the net torque is the sum of all of the torques. If you have a system that looks like this, we have two forces on one side, and they're rotating clockwise, so I'm going to give them a negative number or a negative designation. So the force times how far F2 is away from the axis, how far F3 is away from the axis, that's going to be taken into account. This is basically the torque on the system. We're assuming the forces and the distance from the axis are perpendicular. That's good enough for right now, and it is an assumption. Notice on the other side of the axis of rotation, we've got rotation in the opposite direction, the counterclockwise direction, so we'll give that a positive number. So the net torque is equal to the torque that F1 is producing, and then that's counteracting the torque that F2 and F3 are producing. They actually could be balanced or not. If they're not balanced, then you have a net torque and you have rotation or movement. When you're trying to lift a weight or move an object, if you're producing a concentric contraction, you actually have a net torque, or you could say an imbalance of torques. People sometimes say an imbalance of forces. I really say it's a net force acting on a system. So let's say that the net torque, though, is zero. You have an isometric contraction. You're not extending the elbow. You're not flexing it. The elbow flexors are not able to produce a successful concentric contraction in terms of producing a movement, but maybe they can hold it steady in an isometric contraction. With an isometric contraction, the net torque on the system has to be equal to zero. No torque. That means you have an isometric contraction of those elbow flexors or agonist muscles. So that's how we're going to put torques together. We simply add them up. The key is, though, keep in mind the direction of the torque. Is it clockwise? Is it counterclockwise? Are two torques in the opposite direction or the same direction? So to start putting that together, we have systems to be able to do that. There are three of them, and they are lever systems. So if you've been wondering all this time what the secret of better performance, human movement, sure, there's training, sure, there's nutrition, but in terms of what actually produces the movement, it is forces acting on lever systems. Forces acting on lever systems. That's the secret. Shh, gotta keep it real quiet just between us. This is the secret of human movement system. It's all about lever systems. So lever systems, what they do is they translate forces into torque. And it's a battle in terms of where the net torque or no torque is going to be produced. Is the resistance, does it have a long enough resistance arm or lever arm, or is it the motive force? By changing the force or resistance or the length of the resistance arm and or force arm, we can change the potential of the system to produce torque. And as we're going to see next time, there's often a trade-off between the amount of torque you can produce and then some other factors that we're going to talk about next time. Okay, so that's it for today. You've learned, we've teased you. This is our tease. You're going to be learning about the secret of human movement next time. So we're going to go into some detail about how this occurs. We'll have lots of applications. So have a good one, and we will see you soon.